Good morning, students. Today in this video lecture, we will be discussing the relationship between dilution rate and substrate concentration. Now, as I have already discussed in my previous class of bacterial growth kinetics, that in a continuous culture, there is always an input of medium and removal of waste products. So, two important things has to be kept in constant within the vessel, kept to be taken into account within the vessel, and that is the substrate concentration and the cell concentration. So that is why we need to understand that what should be the relationship between the dilution rate and the substrate concentration. We have already completed the relationship between the dilution rate and the cell concentration, that how the cell varies with the dilution rate. And you know that at critical dilution, that is at the lowest dilution, when the first washout occur, has also been discussed. So first important question over here is that the relationship can be explained by making a material balance around the chemostat on the limiting nutrient. So we have to understand the material balance around or inside the chemostat on the limiting nutrient. So like in the previous derivation, we have an equation. Here also we will have one equation. And that is, we are trying to find out the nutrient accumulation inside the vessel. So that means what? It will have nutrient in. What do you mean by nutrient in? That is amount of nutrient which is being pouring inside the vessel. That is your nutrient in. Then comes your nutrient out. Nutrient out means that how much amount of nutrient is going out of your chemostat. Then comes your consumption. That means how much nutrient has been consumed, right, by the organism to grow. Next is the maintenance. What is the minimum requirement of the nutrient which is being required for the maintenance of the organism? And last but not the least is the product formation. That means how much product, means how much substrate is being metabolized by the microorganism to produce their product. That is very important. So now comes the equation. So if you go into the equation, you will understand that it is ds by dt, that is the rate of change of your substrate concentration in the vessel, FSR by V. So nutrient in has been depicted by FSR by V. What is SR? SR is the limiting nutrient concentration in the medium reservoir. So in the medium reservoir which is being attached with your chemostat, this is the SR, that is the minimum requirement of the nutrient which is present in the medium reservoir, limiting nutrient. Next is your F and V. You know what is F and V, where F is the flow rate and V is the volume of the vessel. And F by V is equivalent to your dilution rate. Next comes nutrient out. That means how much nutrient is going out of the vessel, and that is your Fs bar by V. So now the question is, what is S bar? S bar, I will write over here rather, S bar, the limiting substrate concentration in the chemostat. So till date, SR is the concentration in the seed tank, whereas S, that is the substrate concentration in the chemostat. So again it is Fs by V, right? Next comes the consumption. How much food is being consumed by the microorganism, or substrate is being consumed by the microorganism. And that is your mu x. Why? X by S. What is mu? Mu, as we have already learned in the previous part, that is your specific growth rate, into X, that is the total cell number inside the vessel, total cell number inside the vessel. And Yx by S is the biomass yield coefficient. So when they will consume, they will increase in number. So biomass comes into play. So what is biomass yield coefficient? It is gram cell dry weight formed per gram substrate consumed. That means amount of dry weight which is being formed per gram of the substrate consumed from the vessel. Next comes is your maintenance rate. So we have completed SR, S, YX by S, right? Mu. So next comes your M. What is M? M is the maintenance rate. What is M? Maintenance requirement. Gram substrate consumed per gram cell dry weight per hour. So per cell per hour, how much substrate is being consumed for their maintenance. So that will also be multiplied into X, because maintenance will also contribute to the constant maintenance of the number of the cell. So actually cell has to be related with the maintenance requirement. Then comes QPX YP by S, which is equivalent to your product formation. So QP is the specific rate of product formation. So how much substrate, that is the gram product formed per gram substrate or per liter per hour. So from the substrate how much product is being formed, and YP by S is the product yield coefficient. Gram product formed per gram substrate consumed. Right? So you understand that QP is the specific rate of product formation and YP by S is the product yield coefficient. So there is a difference between the two. So both will depict ultimately the product formation. So this is the overall equation associated with the dilution rate and substrate concentration. Now how can we minimize this equation and make it easy to understand? So in general, if you think inside a bioreactor, this particular mu x yx by S, that is your consumption, of course is very, very greater than your maintenance. So consumption is very, very greater than maintenance. So amount of nutrient for maintenance is less with respect to consumption. So that is why this can be neglected. So we are neglecting the mx, and since we are concerned with the consumption, that means how much amount of substrate has been consumed to produce the product and to produce the biomass. So we are also neglecting the product when no products are there. Thus taking the case when no products are there. So when products are not formed, that case is being taken, and you basically neglect mx, the last two terms, and qpx yp by s, and you simplify the equation. That is your ds by dt is equal to FSR by V minus FSR by V minus FS bar by V minus mu x yx by S. That is simply nutrient in, nutrient out, and your consumption. So that nutrient in will basically be subtracted from nutrient out and your consumption to find out the substrate concentration. So this is basically the simplified version of the equation. Now we will move on to the steady state and non-steady state. Now you know that steady state means when we talk of ds by dt is equal to 0. So rate of change of substrate concentration is 0. So if you put the value 0 on the previous equation, what you get is that, that is your FSR by V minus Fs bar by V minus mu x yx by S. So you see that it will be, if you simplify the equation, you bring mu x yx by S. So it becomes mu x yx by S is equal to Fsr by V minus Fs bar by V. Now you substitute F by V is equal to D. So you just put D over there. So mu x yx by S is equal to D SR minus DS. So you know that you take D as common and you get SR minus S. Now you know from the previous equation where we have related your dilution rate with cell concentration that mu is equal to D. That we have already established. So now if you put the value of D in mu, so what you get? You get basically dx yx by s is equal to d sr minus s. So we can cancel out d. So we can cancel out your d. So as we cancel out d, what you get? You get from previous, therefore rearranging, we get x is equal to yx by s sr minus s. Just you just you cross multiply, you get to see x is equal to yx by s into SR minus S. Am I clear to you or not? Okay. Next we will move on. So from this particular equation, we can have two important conclusions. Equation assumes that the yield coefficient are independent of growth rate, which forms is not always the case. So it is not always the case, but it says that the yield coefficient are independent of growth rate. And it is further assumed that the absolute value of x is independent of all nutrients except the growth limiting nutrient. So the value of x is independent of all nutrients, right? Except the growth limiting nutrient. Am I clear? So this is the first derivation. Now what we do is that we will actually have to give this equation a basic equation of your growth kinetics, that is your Monod's equation. So fundamental equation of continuous culture. So we will move on to the next part, that is your fundamental equation of continuous culture. You see, the equation represents the basic steady-state equation describing continuous culture. It is also necessary to develop a model which relates x, s. So you have to have a model in which you have to relate your cell number, substrate concentration, and your dilution rate, because this is what we are trying to establish: dilution rate and x, dilution rate and substrate. So you should have an equation in which all the three should be related, and this is done by substituting the value of mu in your Monod's equation. So Monod's equation will give you that particular derivation, that particular equation, relation, that is mu is equal to maximum growth rate s Ks plus S, S divided by Ks plus S. So S is the substrate concentration, mu is the maximum growth rate, right? And you know that mu m is the maximum growth rate. So mu can be related to the substrate concentration, a constant, kinetic constant, and your maximum growth rate. Now how will you relate x, S to your dilution rate? Let's see. So, since in both the previous equation we are trying to follow the two important aspects, that is, one is your non-steady state, another is your steady state. So we have to take both the form into account while we are relating this Monod's equation with the previous equations. So for biomass, you have derived, if you remember, you have derived dx by dt is equal to x mu minus d. Now, you have to relate Monod's equation. So just you put mu is equal to mu m s ks plus s. So you have got from the previous equation, your Monod equation is mu is equal to mu m is equal to ks plus s. So you just put this value. What you get? Dx by x is equal to x mu m s ks plus s minus d. So how? Now from here you can understand that you have related your x, cell concentration, your substrate concentration, your dilution rate. So of course you have related all the three terms, right? And you have found out a relation between the three terms. For limiting substrate, this is for cell, for biomass and for substrate. For substrate, in this equation from the previous derivation, what we have seen? ds by dt is equal to d, sr minus s minus mu x yx by s. This was the equation. So just you put the value of mu in this equation. So this is your equation 2. So just put the value of mu in this equation. So this is the value of mu. So when you substitute, what will happen? ds by dt is equal to d sr minus s minus x yx by s. You just put the value of mu, that is mu m s ks plus s. Again you have related your substrate, cell and dilution rate in this equation. So we are trying to achieve our goal, that is relating all the three. And how do they vary? How do they relate with each other? That we could derive from these equations, right? So this is about your non-steady state. Now we will move on to the steady state kinetics. Now, if you see the steady state equation, the most important part of steady state equation, that for biomass the rate of change of cell concentration is 0, that is dx by dt is 0, and for substrate the rate of change of substrate concentration is 0, so ds by dt is equal to 0. So x and s becomes constant and are represented by your x bar and s bar, and you know mu is equal to d, that we have already derived. If you see the equation 1, if you put the value 0, what will happen? You get mu is equal to d. You will get mu is equal to d. So we have got mu is equal to d from equation 1 if you put the value of dx by dt is equal to 0. So now, again the same thing, that is substitute mu with the monods equation. So what is happening? It is d is equal to mu m s ks plus s, right? So this is the basic equation. Okay. Now the question is, you know, that x is equal to, for steady state, for substrate this is about cell concentration, so it is gone. Now for substrate concentration, x is equal to y x by s sr minus s. So here we have not got any value of mu. So how will you substitute, or how will you relate with the monods equation, right? Simply you take this equation, d is equal to mu m s ks plus s, and solve for the equation, solve for s. So you solve for x. So you know that is your, if you just write, I am writing over here, d is equal to mu m s ks plus s. You just solve, that is your, I am solving over here, d is equal to, d is, just cross multiply, ks plus s is equal to mu m into s, right? Okay. So now what you do? Now you write ksd plus ds is equal to mu m s. So now you find out the s. So what is your s? ksd is equal to mu m s minus ds. So you take s as common. So what you get? You get is ksd divided by, you just take this particular thing common, that is your mu ms minus ds. So it will be your mu m minus d. So mu m minus d, this is your mu m minus d, is equal to your s. So you just solve this equation. You just solve this equation by simply cross multiplying d with ks plus s is equal to mu ms, right? And then you just solve for the s. You get this thing, s ksd divided by mu m minus d. So when you get this, you have got s in terms of your mu. So now you can put this s bar, okay? So x is equal to yx by s sr minus this s bar, that is your ksd divided by mu m minus d. So you have put the value over here and you have derived the equation in terms of your monods equation. Okay? Have you understood? Again I repeat that for steady state equation, ds by dt and dx by dt is equal to 0. So as from the previous equation, we know that when you put the value 0 on equation 1, we get mu is equal to d. So that is very easy. And we know that the substitution for mu is mu m s ks plus s, that is a monods equation. So you just substitute mu over there. So d is equal to mu m s ks plus s. But when we go for the cell substrate concentration, you get to see that if you put the value of 0 on ds by dt, you get is mu x yx by s is equal to ds sr minus s. And from there, if you substitute d, the d is basically cancelled, and you know that it is x yx by s sr minus s, which I have discussed in my previous slide. But you cannot relate this equation with Monod's equation as you don't have the value of mu. So for getting the value of mu, we are just solving this equation. This is, say, equation 3, and we are solving this equation 3 for S. So we have simply cross multiplied and have found that S is equal to Ks d mu m minus d. So you just put the value of S in this equation 4. Okay? And ultimately this particular equation becomes your related to your Monod's equation. Now I will move on. So we know that the critical dilution rate DC is the lowest value of D at which washout occurs. And we also know that DC is equal to mu m. We have derived in the last class. However, DC is equal to mu. DC is equal to mu when S bar, that is in the chemostat, substrate in the chemostat, is equal to S. Okay? That is your limiting substrate. This is clear. Since washout, there are no cells remaining in the chemostat, therefore no substrate will be consumed. So they are saying that when there is a washout from the vessel, the microorganism will be removed. So if there is a utmost washout, then the microorganism will be removed. And if the microorganism will be removed, then the substrate in the seed tank will be equal to substrate in the chemostat. Why? Because there is no microorganism to consume that particular substrate from the chemostat. And as a result, what will happen? That means what? SR is equal to S bar. So that is what they are trying to say. Consequently, we write DC is equal to mu m. So that is your DC is equal to mu m SR. SR is, it is the substrate in the seed tank rather than the substrate in the chemostat. So mu m SR Ks plus SR. Hence it is clear that DC varies as a function of SR. Thus, if the value of SR is high, so that means if your SR is high relative to Ks, so value of SR, that means the amount of substrate in the seed tank is high relative to the Ks. So what we do is that we neglect Ks. So this is another equation, say equation 5. So if you just neglect Ks, because Ks is very, very less than that of SR. So what is happening? DC is equal to mu m SR by SR. So Ks is removed. So SR will be cancelled. So SR, you cancel out SR. So what you get? You get DC is equal to mu m. So I have derived what I am saying. It says that when SR is very high, when the SR will be very high? The SR will only be very high when there is no consumption of the substrate. So when the SR is high with respect to Ks, you put the value in the Monod's equation, Ks is being neglected, so SR will be cancelled. And you get critical dilution rate is equal to maximum growth rate. So again, you can relate it with the critical dilution rate where the washout of the cell is occurring from the vessel. So this is all about your continuous cell culture kinetics, where we have related the dilution rate with respect to substrate concentration, dilution rate with respect to cell concentration, and consequently we have related all the three, that is your dilution rate, substrate concentration and cell concentration, in terms of your Monod's equation. Thank you for listening to my class. Stay at home, stay safe, and of course, if you have any questions, any queries, please drop your comments in Google Classroom. Thank you.